Deterministic finite automata. The singular form of automata is automaton. It is defined by the 5-tuple Q, sigma, delta, Q0, and F, where Q is a finite set of internal states, sigma is a finite set of symbols, it is the alphabet, delta is a total function from Q times sigma to Q, this is also called the transition function. Now, delta is a total function from Q times sigma to Q, means that all combination of value of Q times sigma should have one and only one image in the codomain. Q0 is an element of Q. It is the initial state. It is a unique state. F is a subset of Q, is a set of final states. Example 1. Let M be the 5-tuple Q, sigma, delta, Q0, and F, where Q is a set of Q0, Q1, Q2, and Q3. Now these are the vertices in the transition graph. Then sigma is a set of 0 and 1. So it is the label of the edges in the transition graph. Then delta is a set of 3-tuple. Now here we have Q0 with 0, Q0, 0, Q3. So that is in a transition graph from Q0 with label 0 to Q3. Q0 with 1 to Q1. Q0 with 1 to Q1, that's an edge. Q1 with 0 to Q1. So we have a loop here from Q1 to Q1 with label 0. And Q1 with 1 to Q2. And Q2 with 0 to Q1. Then Q2 with 1 to Q2, so that is a loop. Then Q3 with 0 to Q3. Then another one, Q3 with 1 to Q3. So we're just gonna denote like this. Now the initial state is Q0. So we indicate with the arrow like this. Then the final set is Q2. So we indicate with a double circle. So here you have the formal definition on the left, and then the transition graph on the right. Now example 2. Define a deterministic finite acceptor or finite automaton M represented by the transition graph below. So this is the transition graph. Now, so we have to define the automaton by the 5-tuple Q, sigma, delta, Q0, and F. So here we have the vertices Q0, Q1, and Q2. So that's what we get. Q is a set of Q0, Q1, and Q2. Then we have the label 0 and 1. So that is the alphabet. Sigma is the set of 0 and 1. Then we have here a loop from Q0 with 0 to itself. So that is one of the element in the transition function, delta. And from Q0 with 1 to Q1. So we have Q0, 1, Q1. And Q1 with 0 to Q2. So Q1, 0, Q2. And Q1 with 1 to Q2. And Q1 with 1 to Q2. So we're just gonna denote this like this. Then we have a loop Q2 with 0 to Q2. So that's what we get, Q2, 0, Q2. And then the initial state is a Q0, so indicated by this arrow. So that's Q0 is Q0. Then the final state is only one here, so that is Q1. So our F is only a singleton Q1. Now example 3, is the automaton below a deterministic finite automaton? Now this is the automaton. The answer is no, it is not. Why? Because from Q1, we have Q1 with 1 to nothing. So Q1 with 1 is undefined. So we have from Q1 only zeros going out, but H with label 1, there's nothing going out. Example 4, is the automaton below a deterministic finite automaton? So this is the transition graph. Now the answer is no, it is not. Why? Because here we have from Q0, we have two edges going out with the same label 1, but going to different states. So it is not unique. Now, so this is so one of the requirement of the transition function is that function should be a total function. It means that all combination of element of Q and the element of sigma should have only one image in the Q. But here we have two images from the same edges with label 1. So this is not a deterministic finite automaton.